Let's try to understand the savings formula in MMV. Savings is equal to baseline period consumption minus the reporting period consumption plus minus the adjustment. This formula is the foundation of measurement and verification. It's very simple, but that's the foundation of MMV and helps quantify energy savings from an energy conservation measured. Right here, here's what each term means. So baseline gives baseline period consumption. It's the energy usage before implementing the ECM, typically measured over a representative period like a 4-year or a season. Establish the business as usual scenario. If no ECM is implemented, right? That's the baseline. Reporting period consumptions. That's the energy use after the ECM is implemented, and it's measured during the period after project completion, reflect the new energy performance of the system. Then finally the adjustment, right? The adjustment, that it's the normalization adjustment. It accounts for external changes like weather, occupancy, or production level to ensure a fair comparison. If the weather are different, how can we compare? If the number of occupancy are different, how can we compare? Right? So apple to apple, orange to orange. In the adjustment, there's also routine adjustments. Routines adjustments such as that regularly occurred, seasonal variations, that there's always a season change. We are now the winter time, the spring is coming, right? Winter, spring, summer, and fall, and it will repeat. So this is routine change. There's a routine factor change. There's also the non-routine adjustment. For example, maybe there's a new addition to the building. So if maybe an expansion, right, an addition to the buildings, that's a big change, and that doesn't happen every year. So that's a non-routine adjustment. If a change like that happened, we need to account for the effect of that change, right? Or a new equipment is installed. That's not a routine adjustment change. And why are these adjustments important? Again, well, without an adjustment, savings calculations could be misleading. For example, if an ACM was installed in a factory but production also dropped by 20%, lower energy use, is it due to the production reductions, or is it due to the ECM, and how much? Right? So lower energy use might be mistakenly attributed to ECM rather than the reduced productions. Okay. So you can see the graph here. That's the point of the project, the ECM implementations there. Okay. So that's the baseline. After the ECM, this here is the adjusted baseline due to the adjustment that we discussed. And that's the green line is the new measured energy use. Okay. All right. So routine baseline adjustments, right, involve again normalizing energy consumption data to account for independent variables that routinely varied and influence energy use. These adjustments are essential for accurate measurement of savings. Ensure that the baseline that's before the project and the reporting period that's after the project are comparable. Right? Again, seasonal variations that affect by the weather or the number of heating and cooling degree days, right? Humidity, as well as operational variables. So there are lots of variables that can affect energy use, and these are the routine adjustments. The non-routine baseline adjustment address the factors. They are static and that doesn't change all the time, but they affect energy consumptions. Right? These factors can change the underlying energy use profile significantly when they occurred. For example, a change in maybe a factory increase the number of shifts from 2 shifts to 3 shifts. Well, that's a big change, and it doesn't happen all the time. Or again, like we mentioned before, a new additions to the building, right? A major renovation, major modifications to a system, building envelope, HVAC. Okay? So these factors are not part of the day-to-day seasonal variations. They must be accounted for separately. Baseline, adjust the baseline reporting period to the same parameters. Determine energy consumptions if ECM has not been implemented. Okay. So savings, like the stated here, that's the energy avoided or avoided consumptions. Now let's look at another baseline example here. The baseline energy consumption, 500,000 kilowatt hour per year. After ECM, the actual measured energy use is 420,000 kilowatt hour. However, after adjusting for increased occupancy, so number of people increases, and warmer temperatures, the weather changed, the estimated energy use without the ECM would be 530,000 kilowatt hour. So this is probably, say, a chiller system upgrade, right? Chiller system. So what is the baseline energy consumption here? Well, it's given 500,000 kilowatt hour, right? 500,000 kilowatt hour. What is the reporting period energy consumption for 20? So I'm going to write 420 here. Kilowatt hour, right out of space. What's the adjusted baseline? Well, be careful, it's not 500,000 anymore. After the adjustment, it's 530. So we can write 530 here. 530,000 kilowatt hour. So what's the real savings? Right? The real saving before the adjustment, it's only 80,000, but with the adjustment, it's actually 110,000. So the saving here is 53,000 minus the 420, okay, kilowatt hours. So that would be 110,000 kilowatt hour. That's the savings with the adjustment. Well, that's important because we need to know what's the real savings. Okay. So that 110,000 kilowatt hour represent the avoided consumptions. Avoided consumptions. Okay. Scope, measurement scope. Measurement and verification can take different approaches depending on how broadly or narrowly the energy conservation measures are evaluated. Okay, so two key scope here, two key scope. Whole facility approach, that's not the first one. Second one is the isolated retrofit measure approach. So two key scope here. For the whole facility approach, it measures the total energy consumption of an entire building or entire facility, right? It includes the impact of ECM plus other external factors like weather, occupancy, operational changes. How it's measured? Well, use utility providers meter, electricity, gas, water, right? The challenge here is it requires complex adjustment to separate ECM savings from other factors, right? It's not easy to pinpoint which ECM are performing best. We only know the total impact. Okay, but why it's used? Well, large-scale projects where ECMs affect multiple systems like HVAC upgrades and building-wide retrofits, and when we have sub-meters for different zones. Sometimes when sub-metering is not available, then this is the whole facility approach that's when it's used. For the isolated retrofit measure approach, it measures the energy savings of a specific ECM, right? So for example, only the lighting upgrades or only a new boiler, we only measure one specific measures. It includes the consumption within the ECM boundaries, like the system boundaries. We ignore what's outside of the boundary. We ignore outside of our control system, our control volume, right? We ignore the whole, not the whole facility, but we ignore what's outside. So how it's measured? Well, usually it requires new meter or sub-meters to track only that specific equipment affected by the ECM. The example is when we install meters on HVAC systems or lighting circuits or individual machines. The challenge though, it has its own challenge. It needs additional meters, metering equipment, increasing the cost. It's less complex than whole facility, but still requires some adjustment. Okay, when do we use it? When the project focuses on a single energy saving measures, right? And when more precise tracking of a specific ECM is needed. So you just want information on one specific project, one specific ECM. Okay. So here's a table to compare the two key scope, whole facility and isolated retrofits. There are different options that we will discuss later. Right. So whole facility, best for large-scale ECM, isolated retrofit, individual or equipment or systems. So here's the options. Again, IPMVP, the International Performance Measurement and Verification Protocols, defines 4 options, 4 MMV options to quantify energy savings. Right? Each option is suitable for different project types and level of accuracy. Okay, so let's take a look of each one. Option A, retrofit isolation. It's the key parameter measurement. So what does that mean? It measures only the key performance parameter that drive energy use, while making reasonable estimates for other factors. Right? How does it work? Well, it directly measures certain critical variables such as the power use of a motor. Okay, we will be doing that, the lab, to measure the power use of a motor as well later on in the lab. It uses assumptions or past data or engineering estimates for some key parameters like runtime. Right? Example, say if we have a lighting retrofit where only wattage reduction is measured, but the hours of operation are only estimated, right? We don't measure the hour of the lighting system is on or off. Okay, so the advantage here is the lower MMV cost, lower cost, but it's good enough. It's good enough for the specific ECMs with predictable performance, right? The disadvantage, well, accuracy depends on how well the assumptions are. Okay, how well the assumptions represent, match the reality, right? Option B, retrofit isolations, but now we measure all the relevant parameters. It measures all relevant parameters to determine savings, avoiding some of the assumptions, like in option A. Right? It uses meters, sensors to track both energy use and operating conditions. How long, how much. No assumptions, right? No assumptions or no estimate, like in option A. So more accuracy than option A, but also a higher cost. So for example, if we install a VFD, right, where the power draw is measured maybe for every minute in this case, and we'll be doing that again in the power logger lab, right? Power logger lab. Okay. So higher cost, but more accurate. Option C, whole facility measurement. It measures the total energy consumption at the facility level, so higher level now, not individual, right? Before and after, both before and after ECM implementation. It uses utility provider meters, like the electricity bills, gas, natural gas, water. It does require adjustment, right? It does require adjustment for weather, occupancy, production, right, so on and so forth, to isolate ECM savings. Okay, to isolate ECM. The example is a building-wide maybe HVAC and lighting upgrade where savings are determined by comparing total monthly electricity bill before and after the retrofit. Okay, the advantage again, it captured the all ECM interactions. For example, lighting. The lighting use affects HVAC. How is that? Well, less heat from lighting systems, right? All the lights end up as heat. And if we reduce the lighting use, the energy use, it also reduce the heating, it reduce the cooling loads during the summertime, but increased, what did I say? Let me correct myself. So the heat from lighting systems will increase cooling load during the summertime, but reduce the heating load in wintertime. So the building systems, HVAC and lighting system, that have effect, right? The lighting system use will affect HVAC as well. So this method will capture all the ECM interactions and system-wide impact. The disadvantage, well, how do we quantify the savings from lighting system alone or from the HVAC alone? It's not easy, right? All right. One last options, option D, calibrated simulations. Let's talk about it. What it does is it uses a computer model of the building or system to estimate energy savings. Why? A detailed energy model is built based on building characteristic and energy use patterns, right? The model is calibrated using measured data, utility bills, temperature sensors, and savings are determined by simulating the building's energy use with and without the ECM, but both in simulations. Okay. So one example is energy retrofit, where a full building energy model is created in software and calibrated using real data. Well, the advantage, why is it used? Well, because it can be the only method we have, right? The only method we have. The only method available when pre-retrofit data is missing. For example, if it's a new construction, where do we get the data, right? So it's good when we don't have the data, then we can use this method. It can provide insights on savings potential before the implementation. So if you are going to construct a new building, how are you going to decide? Okay. The disadvantage, it requires expertise in energy modeling, and we know it's not easy to model, right? I mean, we have some investment in this field, but it can be difficult sometimes. Higher cost is another disadvantage, and very time intensive to create a model, or time intensive to create a good model, right? Okay, so A, B, C, D, 4 options. Look at a comparison here. So in general, the cost will go from low to mid to high. Option A, B, C, D. Option A, you only measure key parameters only, right? So relatively low cost with some assumptions. We don't make, when we simplify the MMV, right, based on some assumptions. Then move to the all relevant parameters. That's option B, whole facility, option C, and the whole facility modeling, right? So you can see the accuracy also go from mid-high to it varies because it depends very much on the model. Okay, very much on the model. Okay, best for different scenarios, right? As we discussed before, for simple projects where the savings are very much predictable, okay, compared to sometimes there's more interactions between systems and equipment to where when we don't have the previous data or when it's a new construction. So again, you can look at the comparison in this table here.